All right, we are right at the start time, 2 o'clock Eastern Standard Time, so we'll go ahead and begin. First off, good afternoon. I'm Jason Thomas, project engineer at America Makes, and I'll be your host for today's America Makes TRX webinar series. A little background on the TRX webinar series before I introduce our speakers. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium called the America Makes Technical Review and Exchange webinar series was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with a broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can contact the America Makes TRX webinar series administrator, Jason Thomas, directly. A few important notes before we kick off the series. At the end of the presentation, there will be an opportunity for a brief question and answer or Q&A session. If during the presentation you have a question, please submit it in the Q&A space on your WebEx screen, and I will ask it during the Q&A session. I'll do my best to get all of your questions answered. Today's webinar, excuse me, today's webinar is on DigitalClone for additive manufacturing. Without further ado, it is my pleasure to introduce Melissa McReynolds and Dr. Behrouz Jalalamadi of Sentient Science. Melissa McReynolds is a Senior Vice President and General Manager for Sentient's Automotive Business Unit. With a primary focus on DigitalClone for engineering, DigitalClone for additive manufacturing, and DigitalClone for in-situ monitoring, prior to joining Sentient Science in 2018, Ms. McReynolds was a senior growth leader for Honeywell Aerospace, where she led cross-functional teams to ensure pursuit and proposal execution, revenue attainment, and profitability for over $6 billion of business. And in her early career with Honeywell, Melissa provided leadership to engineering and shop personnel to meet operational demands and customer requests, all while reducing cost and repaired and overhauled components. Prior to Honeywell, Melissa led the 767 and 777 aircraft systems engineering team for American Airlines. During her tenure, she designed and supported maintenance and modification projects on major aircraft systems, fuel, hydraulics, pneumatics, and air conditioning systems. Ms. McReynolds holds a bachelor's in mechanical engineering from Queen's University in Ontario, Canada, and an MBA from Samford University in Birmingham, Alabama. Dr. Behrouz Jalalamadi is the Vice President of Additive Manufacturing and Life Prediction Technologies with Sentient Science. He graduated from Purdue University in West Lafayette in 2010 with a PhD in mechanical engineering and then joined Sentient Science. Since then, he has taken various roles in both R&D and commercial delivery. In 2015, Behrouz formed the additive manufacturing team at Sentient and has been the team leader since then, working on various AM projects and developing Sentient's DigitalClone for additive manufacturing platform. He has been the principal investigator for multiple SBIR Phase 1 and Phase 2 projects. Also, he is the lead scientist for development of the components life prediction integrated numerical solver and support of life prediction projects and validations. His expertise includes fatigue, additive manufacturing, material microstructure, tribology, damage mechanics, modeling, and simulation. Behrouz has presented in various technical conferences and has published multiple peer-reviewed journal papers. Melissa, Behrouz, I will now turn it over to you and your team.
Thank you so much, Jason, and thank you to all in attendance for taking time out of your day to join the first America Makes TRX webinar of 2023. We certainly appreciate you being here and hope that you find our technology not only fascinating and intriguing, but useful for your AM practices. As Jason mentioned, I'm Melissa McReynolds and I lead Sentient's Additive Manufacturing Business Unit. And in a little while, I'll turn it over to Dr. Jalalamadi to walk through the technical details of our offering. First, I'll give you a brief history of Sentient Science. If you're not familiar with us, our core technology is named DigitalClone, and it was primarily developed with funding from the US government through the Small Business Innovation Research Program, also known as SBIR. We were awarded many programs from several different agencies to develop a microstructure-based approach for simulating the fatigue life of components. It is a physics-based modeling tool that simulates the microstructure of different components and their behavior, calculates internal stresses caused by different applied loading conditions, accumulates internal damages resulting in crack nucleation and propagation, and then ultimately investigates the performance and predicts the life of those components. Several years ago, we realized that the same methodology could be applied to the emerging market of additive manufacturing. So we developed a suite of modeling technologies for metal additive manufacturing, including predictions for the grain structure, residual stress, porosity, distortion, surface roughness, and ultimately our proprietary model to predict the fatigue life of additively produced parts computationally and virtually rather than with physical printing and testing of the parts. Accelerated by the NASA STTR program, which is the technology transfer program done in partnership with research institutions and universities, we were able to package all of our additive manufacturing technologies into a software application called DigitalClone for Additive Manufacturing. So it's a unified software package that encompasses all of our work on the additive manufacturing-based technologies. This slide just shows a timeline of our work with the different government agencies dating back to 2004, where we started developing our core technology to model things like propulsion systems and drivetrain bearings to determine remaining useful life of those components and systems. And then we worked towards developing other products like prognostic and health management technologies for UAVs and fatigue crack initiation predictions for rotorcraft spiral bevel gears. And then, as I mentioned later on, we started development of our AM software in 2016. So DigitalClone for Additive Manufacturing is a multi-scale, multi-physics software as a service model to computationally assess quality and performance of additive manufactured parts. DCAM, as we call it with an acronym, uniquely links the process, microstructure, and fatigue aspects of the models to provide design and computational testing, thus reducing the necessary physical tests required to qualify a part. So as I mentioned, I'll give a high-level overview and then I'll pass it to Baruz to dive deeper into the details and answer any questions you may have. But before I do that, I'd like to highlight a recent achievement and brag on our scientists here at Sentient, like Dr. Baruz, who's on the line for just a little bit. So last summer, NIST held a challenge for blind simulation predictions for laser powder bed fusion production. The competition focused on modeling and predicting different aspects and features involved in additive manufacturing, from process to materials to microstructure and properties. Sentient's team submitted DCAM simulation prediction results for 6 different categories and competitions in the AM bench competition, and we were awarded 4 first-place finishes in the AM bench challenge. So this just provides and proves that it was a blind validation of our technology using benchmark data, and shows not only that the completeness of our AM modeling solutions, but also the accuracy of DCAM's predictions. All right, so again, high-level overview, and then I'll pass it to Baruz to go through each module individually. But overall, our ICME platform is physics-based, and it consists of 3 modules shown here on this slide. So we have a process module, microstructure module, and then fatigue performance. It's considered to be prediction technology to address key issues in the manufacturability of additively manufactured parts. The capability allows users to optimize build orientation and support structure designs to achieve the first time right print. So in the process module, we simulate the part level distortion and residual stress with respect to various key process parameters. And then next, knowing that compared to conventional manufacturer components, additive manufacturer components have a unique microstructure that affect their mechanical properties and durability. So in our second module, we're able to use a limited set of machine-specific calibration parameters to predict the microstructure of that additively produced part at a microscale level. And that lets us predict the grain size, grain structure, and porosity of parts created using laser powder bed fusion. And then third, our proprietary fatigue model predicts the fatigue performance at the grain level, considering variations in defects exhibited microstructurally. So here in this module, we're able to simulate the fatigue performance of the AM component at specific mechanical loading conditions. And all this is done using Amazon Web Services, high performance computing resources. We host our software on the cloud for fast simulation, and you'll see an example of the speed of that a little bit later. So at this time, I'll turn it over to Baruz now to discuss the details of each module in DCAM in more depth. Baruz?
Okay, thank you. Thank you very much, both of you, Jason and Melissa, for the introduction and early discussion of the technical content here. So again, yeah, good afternoon, everyone. In continuation of what Melissa was mentioning, of course, as you saw those three modules in the previous slide, those are the three modules that almost everyone agrees that we need to have in a comprehensive ICME solution if you want to be able to start from the material properties and get to the performance of that part. We need to have those different modules to simulate different parts. And of course, as you saw on that slide, by its nature, it's basically a multi-scale simulation package that each of those modules are working at a different physical scale, going from the full component to the very small RVE in the grain level. So to give better understanding of each of those modules, I have a couple of slides for each of those modules here that I will explain how they are working, and then of course show you some of the kind of validation result compared to physical data that we have gathered over different projects. So starting with the first module, which was a process modeling module, as also starting the conversation, as you can see here on the right hand side, the right hand side is basically the snapshot of the actual DCAM as we are offering to the customers. As you can see, the design of the software, the GUI of the software, it is basically in a way to look like a lot of other finite element or CAD packages that are out there that are very user friendly for most of the mechanical engineers. That you can see, yeah, we have a main window that of course the operations, the graphics are showed in it. Below that one, of course, we have the output window, and then on the left hand side we have the tree of buttons that the user can select to communicate with the software and go through different operations. So in the process module, what we do is, of course, as it is shown here in the bottom picture, is that we are starting from two sets of parameters. One of them are process parameters, the parameters that user sets on the machine, like laser speed, laser power, the thickness of the powder layer. All of those parameters that you have to set on your machine to make a part, basically we are also requesting them as the input for this module. And then, of course, we have a set of material properties. The set of material properties, again, some of them are already available in our library that I will explain a little bit more in details later on during the presentation, but also we ask a couple of material properties for the user to make sure that we are as close as possible to their actual material. And then, of course, another piece, which is obvious, is the geometry of the part. What part is going to be built. So we also import the geometry, like STL file of that part. And then after that, of course, we do the simulation. As you can see here, the simulation in this stage is based on inherent strain theory and, of course, computational finite element. We do layer by layer simulation. And at the end of the simulation, the results that are available here in this stage are the distortion and the residual stress that are left in the part during the build, because of course we are working with the thermal process, and because of the with the sharp, big, intense thermal process, and because of that thermal process, of course, we're going to have distortion and residual stress that are left in the part. Which one of the goal of this first module is basically go through different design that the user might have to see how they can minimize those distortion and residual stress that comes out of the machine. There is on the third bullet here also, as you can see, again, this is a module that need to be calibrated for any combination of materials and the machines. And of course, in our library, we have a few of those already calibrated material card that, again, it's a combination of material and machine. And if the user comes to us with a new combination of a material and machine that we haven't already worked on it and it is not in our database, of course, we have to do the manual calibration for them, and then once that is done, we add that one to their material library, and then they can use it. And of course, that part is confidential, and any new material that they want to work on, it is only available to them, not to the rest of our customers. Go to the next slide, please. So here, as I was explaining, so here in the bottom row, you can see the different stages that are involved in the process modeling. Of course, again, as I explained, the first stage is that calibration of the melt pool. And again, of course, we are asking if it's a new material. Of course, we are asking a few samples from that built from the customer, so we can do the calibration. Once the calibration is done, then after that, of course, we have our microscale thermal mechanical that we do it on a simple geometry, like a simple cube coupon, as you can see here, like a simple cube or a L-shaped bridge. But then after that, those information, of course, are used for the full scale, full geometry of a part that is basically built with the same machine and the same material on the same facility. So they can using it for, after that, you can simulate the full level component. Again, the AM parameters that are requested to be imported are listed there. And then on the upper right hand side, you can see one example of comparison of our computational prediction through DCAM versus the actual physical experiment for the, again, same material, same machine. And you can see that here there is a good qualitative agreement between them. For the other modules later on, I will show more quantitative comparison. For this one also, I have more competitive comparison, but most of them are IP restricted and priority for our customers, so I can show them there. Go to the next one, please. So as we are starting the second module, microstructure modeling module, one of the output of the first module is the thermal history in the part. As we are doing that thermal analysis layer by layer of putting the powder and then passing the laser, and of course we are simulating the melting and re-solidification of the part. We have one of the output, of course, is the full thermal history. That means that at every location in the part at any time, we know what was the temperature history there. That's the input, that's the output from the process module, which would be used as the input for our microstructure module here. Now that we have those information, and of course, as we have the material properties, now we use a cellular automata model to translate those thermal information and material properties to the microstructure that is created after the solidification of the melted pool, and basically what is the microstructure that comes out of the machine. Of course, we all know that prediction of the microstructure for the entire part computationally is impossible as of today, at least with the current computing speed and resources that we have. That is a model that will run forever. So instead of that one, what we do, of course, is we are focusing on a small RV in the part that basically users select that, where is my hotspot that I want to do my microstructure simulation, and we predict the microstructure for that location in the part instead of the entire part, again, because it is computationally impossible. And that RVE, a small RVE, as it is shown here on the right-hand side, later on can be used for material inspection and microstructure statistical analysis, or it can be used as one of the input to our fatigue simulation package. Go to the next one, please. So on the right-hand side, as you can see here again, similar to the first stage, both process module and microstructure module, as you can see, both of them are iterative process that we are going through the layer by layer of adding the powder, passing the laser, simulating the thermal phenomena, and then of course coming back to the solidified part. And you can see two view from the side and from the top as the laser passes and how the microstructure is being created, which obviously you can see in those figures the effect of the laser passing orientation on the microstructure. On the I hear some background noise. I'm not sure. As you can see on the lower left-hand side, I just want to show one comparison of what we predicted through our simulation versus what has been reported under microscope. So of course in the middle column, you can see we are working with the ideal condition. That means that we are working with the optimum set of parameters that normally is provided by machine OEM for every material. If we do that one, as you can see, both in the experimental work and on our prediction, we are predicting a very clean microstructure. But as we deviate from those optimum set of parameters, going toward both lack of enough energy or too much energy on the left hand side and the right hand side, as you can see, our simulation predicting the presence of different level of porosity, as it's of course happening also in the physical samples. In the middle also, I'm showing one of the output that is available from our simulation, the microstructure module. So again, as you saw in the previous slide, the morphology and the graphical distribution of the microstructure is available, and then of course we are providing statistical outputs like the grain size average and the distribution and the porosity percentage in the microstructure. Go to the next one, please. Here I wanted to show a few different validation of our microstructure module that we have done over different projects. As you can see here, they are for different type of materials and different type of printing strategy to show the flexibility of our model and and its compatibility again to different materials and different printing strategy. On the upper left hand side, as you can see, specifically I wanted to show you this case that although that both of those samples, experimental one on the top row and the simulation in the bottom, although that both of them are for print of Inconel 718, but in the physical work, which is also as it is mentioned there, it's open literature and it is not our own work. They tried two different set of parameters for the same materials, and they show with their EBSD imaging that the microstructure is different for both of them. Again, although they are same material, but of course, as we all know, because of effect of different printing parameters. So we do the same thing. We use the same material property set, but we change and follow their two different set of machine parameters. And obviously, you can see the responsiveness of our model to that change of AM process parameters. On the upper right-hand side, you can see again the comparison of our prediction versus the experimental build of aluminum silicon alloys. As you can see, we have both a very good comparison, both qualitatively and quantitatively here between the microstructure that we predicted versus the microstructure that was observed under physical EBSD. Coming to the lower section on the left-hand side, again, as I explained it a bit in the previous slide, I wanted to show you the responsiveness of our model to the set of the parameters that you are giving as an input to the model. Again, as you can see, if you are close to the optimum set of parameters like 300 watt laser power here, we are outputting, of course, a very relatively clean microstructure. But as we deviate from that optimum power level on both sides, going to the lower energy or higher energy, of course, again, you can see the formation of porosity in our microstructure. Same thing on the right hand side, lower section. Again, I just wanted to give you some quantitative comparison that, again, for aluminum silicon alloy, using different set of parameters, what happens in terms of, presence of porosity inside the microstructure and the experimental measurement versus our predicted values from our simulation. Go to the next one, please. So now we are entering to the third module, which is basically a fatigue modeling toolbox, which is to simulate one of the major performance of a part once it is in the field, right? It is about fatigue, how long this part is gonna last under under the real world loading that is gonna go through. Of course, you can see the chronological order of these modules. That first of all, we have to make a part that comes right out of the machine, right? It doesn't have excessive residual stress or distortion left in it. It has a nice microstructure with not that much of porosity in it. And then finally, we get here that, okay, if we have satisfied those two first conditions, now we are ready to sending it to the field. How long is going to last? To this one, as Melissa mentioned, we are using our component life prediction technology, which is our patented technology that has been developed for, as you saw in one of those early slide there, that has been developed for more than 12 years now. And of course, again, originally it was developed for traditional materials, and then after that, of course, we saw the potential, and then we extended it with the required R&D work to our additive manufacturing parts. So here, the work that in the next slide, I will talk a little bit about the technology, but here I wanted to show you the type of the output that are available from this module. Of course, on the right-hand side, you can see a very familiar SM plot. Stress to life plot, which is very familiar for every mechanical engineer, that of course, what is the expected life under each level of loading. And of course, in general, we know that as we increase the load level, we're gonna get a lower life. As you can see on that SN curve, similar to experimental work, we are not providing only one data point, because we all know for fatigue, that's kind of meaningless. You cannot put one single life value for a load level, because we all know that the fatigue by nature is stochastic and is sensitive to quite a few randomness in different parameters. And when we are talking about surface roughnesses, we are talking about the loading, we are talking about the microstructure, all of them have randomness involved with them, and because of that one, the fatigue again by nature is stochastic and random. That means that, again, if you make like 10 dog bones, put them under the same loading, you're going to get a range of fatigue life instead of a single value. That's exactly what happens also here in our simulation, that we, as you can see on the SN curve, even for a fixed load level, we are providing a range of fatigue lives, which later on can be used for any statistical analysis, for example, for viable statistical analysis, as it's shown here on the left-hand side. That during the viable, then of course you can provide or calculate your viable slope, which is a measure of how much scatter you have in your set of data, and then also you can produce L10, L50, those statistical life values based on your application. This is also something that is of course provided here through our DCAM. We are providing the viable parameters when the simulation is done. Go to the next one, please. Also, one output that we are providing is the gallery of crack animations and final crack formations. Again, here on the right-hand side, you can see one of those animations, which is again provided through the GUI here. And then also, for example, if you run 30 different simulations, all of those 30 simulations, you would have access to their crack animation gallery. And I just wanted to show two different samples here in the bottom. As you can see, not only the fatigue life itself, but also the crack pattern, of course, it is affected by the microstructure of that specific domain. These, like when you're running 30 domains, all of those 30 domains have the same average, statistical average behavior in their microstructure, but in details, they are different. And those differences in the details are causing, again, that variation in both fatigue life and the crack patterns. On the left-hand side, I'm showing again that component life prediction technology. As I mentioned, it is patented, and it is based on damage mechanic, and it is not based on fracture mechanic. And I like to emphasize on that one, as a lot of other computational packages that are providing the fatigue life, they are working with fracture mechanic methodology. Which is different than what we use. Again, we are using damage mechanic. The biggest advantage of damage mechanic method compared to fracture mechanic is you do not need to have any initial crack in your model to start from that one and see how that crack is going to propagate and how long you have until the failure. Instead, in damage mechanic, you start from virtual pristine materials, in the sense that, again, you do not need to apply any crack there. There could be defects in the microstructure, of course, porosity, inclusions, voids, or even small cracks, but you do not need to apply that one. And then you start from the damage that is accumulating at the grain level, on the grain boundaries. And then, of course, those damages are growing, becoming more, creating dominant cracks. And then finally, those cracks convert to long crack that causing the failure. What is the advantage here? The advantage here is that with this kind of damage mechanic methodology, you could simulate the fatigue crack initiation stage, something that fracture mechanic methodology is missing. And as we know, when we are talking about high cycle fatigue, in almost 90% of the case, most of the life is spent actually in that crack initiation stage. Especially if you're working with the sensitive applications like aerospace. So the tool that we are providing here, the good thing is that is providing the life for the crack initiation stage of the part. Go to the next one, please. So I have a couple of validation now for the fatigue module here. One of them, of course, as you can see here, this is basically as a mechanical engineer, you know that this is the simplest case of mechanical fatigue that you could do, as the simple dog bone, round dog bone under axial loading. The dog bones are made from 17-4 pH stainless steel through, of course, a laser power bed fusion. As you can see, the prediction of the microstructure in the middle, and then of course, we are putting it under axial loading and getting a range of the fatigue lives. On the right hand side, you can see the comparison of our prediction versus the experimental measurement that we did on the same sample. So we experimentally manufactured a few samples, put them under the fatigue loading, and then also we did the simulation. So as you can see, our prediction is wider than the experimental data. The reason for that one is that as we are doing the simulation, basically the microstructure that we are creating, we are trying to create kind of like from the worst case scenario to the best case scenario, that what would happen if you are not lucky and your microstructure is the worst that it could be, and what would happen if it is the best that it could be. And then, of course, as you can see, the experimental behavior is right in the middle of that range. Go to the next one, please. For the next one, I have a little bit more complex geometry. It's still not that much. It still is at kind of a coupon level. It is a single gear tooth under bending fatigue. You can see the experimental setting that was used on the left-hand side. Also, you can see one of the broken sample in the bottom, and you can see the crack started and propagated close to the root of that gear tooth. And then, of course, we did, again, our both the physical manufacturing and physical testing of this sample, and also the simulation. Here now on the right-hand side, you can see that as we are getting to a more complex part, because of the more complexity in the geometry, of course, your microstructure is going to be also more affected by that one. And because of that one, you can see that compared to the previous one, even the experimental data now has a wider range. And then again, as you can see, that range falls inside the prediction that we are providing for this Ferrium C64, which is a high strength, aerospace grade steel. Go to the next one, please. Of course, we have even validation for more complex geometries for the fatigue one, but again, most of them are done for our customers, and we have IP restriction for almost all of them, so it's hard to show the result here. I just wanted to show you some generic result that can be used as the baseline. On this slide now, as Melissa mentioned at the beginning of the presentation, I wanted to give you some software information that, and the computational, idea about the software. So again, as Melissa mentioned, we are providing DCAM as a web application that basically it is sitting on AWS upstream services. So instead of you installing anything on your machine, you will access to that online platform. There are a few advantages for that one, of course. One of the advantages is that you do not need to be worried about your available computational resources that you have, because we are using AWS, so virtually it is unlimited computational resources. Another one is that, again, you do not need to be worried about the compatibility issues and any like packages that you might be missing. Everything has been, of course, already configured on that machine. And another advantage is that in that way we can provide 24/7, troubleshooting and updating the package. Whenever you have a problem, we can always, fix that problem and pushing it, instantly, instead of sending something for you to, download and do any patching. There is, of course, most of the customers are asking, there is one issue with the security of the data, which is a valid question. Of course, again, we are following all the security protocols that Amazon can provide on their AWS platform, but also the user has the option of running either on regular AWS or on the GovCloud. GovCloud is again, AWS server that Amazon is providing, which is compliant with all of the ITAR restriction imposed by the US government. So again, that one is backed by those standards. So if you have something that need to be run in that environment, you can always use that ITAR GovCloud services that Amazon is providing, and we are providing it through our software to the user. So again, speaking of how much timing we are talking about this computational package, of course, you can see some numbers here that for the first module, we are talking about, a couple of hours. For the microstructure, we are talking about a little bit longer, 7-8 hours. And then for the fatigue, as we are running all of those multiple domains parallel to each other, then we are talking about 5 hours to 10 hours time limit. Of course, all of these numbers are affected by different level of complexity that you might have, right? How complex is your microstructure? How complex is your geometry? How many simulations you want to do? How many loading data points you want to create? So all of those, of course, will affect, but I just wanted to give you some idea about, when we are talking about the computational framework, how much time it's going to take. Go to the next one, please. I think your computer is doing the update at the wrong time.
Did you want me to switch the presenting privileges to you, Baruz?
Sure, that's probably the right thing to do. I think, yeah, probably the computer got
Okay.
frozen on Melissa's end.
All right, no worries. All right, go ahead. All right, thanks everyone for sticking with us.
Okay. So sorry for that. So again, continue on that one. So on this slide again, kind of as a kind of summary, I wanted to show you, summarize in one slide the different type of outputs that are available through different modules that are there. Again, I talk about a few of them. You didn't see a few of them. I just wanted to give you some idea. For example, as you can see here in the bottom, this is a porosity map that we are also providing to our users, that basically user can choose two different parameters and for the variation, and we run multiple simulation, kind of a DOE, to create that porosity map to give the idea to the user that where they have to move their parameters to get a better porosity, and where they might get a worse one if they move toward that one, to help with their design to get a better cleaner microstructure. Again, statistical analysis of the microstructure itself, Weber plot, SN curve, and then of course the presentation of the residual stresses and the distortion that are left in the part during that, of course, thermal process of AM printing. Here, as I mentioned before, is basically kind of a list of the current library that we have in DCAM, the different type of AM machines that we have worked, and different type of AM materials that we have worked. You can see that we have worked on a lot of typical AM materials that are used in the industry, from titanium 6-4, different kind of Inconel, different kind of stainless steel, and then of course a couple of aluminum alloys. As you can see, of course, there are check marks here, because again, as we are doing our calibration process, we believe that the calibration need to be done for the combination of material and the machine. And if it's the same material but on a different machine, we have to do calibration to make sure that the result that we are predicting are accurate for that specific machine. And again, if it's something that we do not have in our library, we work with the user to do a few experimental build. We took those samples, do our internal material calculation on them, do a couple of simulations to do the calibration, and once that is done, that calibrated new material card is added to our software. And again, if the user says that this is proprietary and cannot be shown to anyone else, we do not show it to anyone else, and it is private to that customer. So in summary, I showed you, as Melissa mentioned, DigitalClone is the branding name that we are using for all of the different computational packages that we are providing to our customers for different applications. Today, we specifically talked about DigitalClone for additive manufacturing, or DCAM, which is specifically designed to help the user to make a better part through going different what-if scenarios that he might have in his mind, and to do better qualification. As you saw, this ICME package has 3 modules: process, microstructure, and fatigue. Each of them are using relevant physical methods and theory to come up with the requested outputs, which again, the major outputs were residual stress and distortion, microstructure and porosity, and then of course performance, i.e. crack formation and fatigue life of that part. Again, I showed you a few validation here. We have many more of them. We also have a journal peer-reviewed published paper on this one that you can access to that one, that there are more validation on that paper. And then also, again, what is the bottom line? The bottom line is this computational package, of course, can never replace the physical validation and physical qualification, but instead it is trying to, of course, help the user to reduce their time and cost as they are going through their design process and their qualification process. Again, they can try many more what if scenarios that they have in their mind for different, design idea that they have to see which one is going to be the best one probably, or narrowing it down to just a few options, and then also make their qualification process again cheaper and more optimized. So by that, thank you very much for your attending this presentation and listening to me. Hopefully it was something interesting that you saw here. And then I think now back to Jason and Melissa, as we are, I think, have a few minutes for Q&A.
Yeah, great. Thank you very much for that great presentation, Melissa and Baruz. It was great. So we'll now head into the Q&A session. If you have questions for our presenters and you haven't done so already, go ahead and type it into the Q&A box. We did get a lot of questions during the presentation, so I'm going to go ahead and just jump right in. So our first question is, can the output of the thermal modeling be saved on its own as temperatures and or cooling rates?
Very good question. As of today, no, that one cannot be reported as independent output. No, we are only reporting residual stress and the deflection.
All right, thank you. And then is there an option for non-cloud-based computing?
That's of course a question that a lot of our customers asking about that one. That's something that is on our roadmap, and we are working on it, but it's not going to be available in the near term future.
Okay.
I'll just add that, if there's concerns about the security of data and such, I think Bruce touched on it nicely during the webinar, but also, GovCloud is an option, which has more stringent security measures. And then by making it a non-cloud based computing software, you would lose the access to the high performance computing resources that AWS provides. So it would be utilizing your own computing resources for the computation.
All right. Thank you for those extra details, Melissa. Okay, so let's see. Let's move on to the next one. Can the software currently, or are you planning to predict other mechanical properties besides fatigue life, such as impact toughness or tensile strength?
Right. Very good question. As to be able to predict those, of course, we need to do core R&D. So a few of such features are under R&D in our, in our group, but also we have already started conversation with other people that, of course, have worked on those to save some time. So we are hoping that, of course, yeah, we extend our collaboration with those groups that we can offer those kind of, mechanical property, let's call them mechanical property prediction even in our package. But again, it is on the conversation stage as of today.
All right. Thank you very much. Let's see. So let's see. Microscale thermomechanical modeling uses inherent strain approach as well.
Can you repeat that, please?
It says microscale thermomechanical modeling uses inherent strain approach as well. I think this came in, I can't remember what slide it was on. I was trying to
Yes.
catch that.
Yes, it's still using that methodology. Yeah. So it is basically used for kind of two levels. Yeah, for both micro level and the macro level. Yes.
Oh, okay, great. Thank you. All right, let's see. Okay, so for how many alloy systems has the computational data been validated through experimentation?
Right. So as you saw on that list, that basically these are the different alloys that we have done the validation. As you can see, all of them are single phase metallic alloys, except the titanium 64, which is a two-phase metallic alloys.
All right, great. Let's see. Can you compute the thermal time history of a specific array of points in a specific layer that can be used to compare with in situ monitoring data for a laser powder bed fusion print?
Very good question. And actually, that will start a completely new conversation that today I showed you our DCAM. We also have another additive manufacturing computational package. We are calling it DCIM, DigitalClone for in situ monitoring. So that's something that is the combination of hardware and software, of course, because we are talking about in situ monitoring. So that's a package that we have developed. It is, and we are just offering it as a commercial package that basically do both in situ detection and in situ repair of any defect that is happening during the build. So to answer that question, yes, we have that technology. It is not under this product, it's another product. And if you're interested to talk about it, please reach to us and we can show you, that technology.
All right, great. And yeah, we're going to give you that contact information here in just a minute. Let's see. So how are the effects of flaws or surface roughness accounted for in the models?
Very, very good question. Again, the advantage of this type of damage mechanic approach is that again, we are not telling to the solver that where is the bad area, where is the weak point that the failure is gonna start there. Basically, all of those competing factors are already in the microstructure. In the microstructure, you might have some grain boundary mismatch, you might have inclusions, you might have porosity, and also, of course, you have the surface roughness effects. So they're all there based on their severity relative to each other, and based on the type of the loading that you're applying there, and then, of course, based on the material properties, they are competing with each other. And at the same time, the damage mechanics solver is calculating damages for all of them. And with repetition of the load, each of them is, getting more accumulated damage until one of them, or maybe a few of them at the same time, reach the critical damage level. Then, there is a macro crack created there. So again, they are all available there. They are competing with each other. They are all accumulating damage. And once the damage passes the criticality, the first macro cracks are creating, causing even more stress concentration. And of course, with the repetition of the load, those cracks are growing and causing the failure.
All right, thank you very much. Very detailed answer. Okay, let's see. Can you connect your grain nucleation and growth to the thermodynamic and kinetic aspects of phase formation near the melt pool for laser powder bed fusion?
We haven't tried that. Very good question. Other people have asked that one too. We haven't tried it yet. No.
Okay. Let's see. What kind of microstructure parameter was changed in the graphs in slide 16 and 17 for given bending stress?
Okay, so as I was coming back, sorry, can you repeat the question, please?
Sure. Let's see. What kind of microstructure parameter was changed in the graphs in slide 16 and 17 for a given bending stress?
I'm trying to answer it in the way that I understand the question because yeah, if you're talking about the scatter that we have in the data here, I'm assuming that's the question, that why we have a range of the domains and like what's the difference between them. Again, those domains for the same load level, they have the same average behavior. That means that, for example, if you have 2000 grains there, if you plot the grain size distribution, those grain size distribution, of course, are going to be different for each of those 20 domains. But if you calculate their mean value is same. So again, their average behavior is same, their average orientation, their average size is same. But every single of those grains, when they are sitting next to each other for those 20 different domains, are different. And that's how we are getting the scatter in the SN curve. I'm hoping that that was the question.
All right, thank you. Yeah, if the person who answered that question, if you want to, send me a chat here quickly, if you're interested, um, and just let me know if that answered the question or not. If not, if you want to clarify it, I could try again if we have time. I think we have one or two more here. What are the worst and best scenarios of the microstructures for fatigue simulations? Do we need to change process parameters or material properties to have this variation?
Very good question. So you do not explicitly determine what are the worst case and what are the best case scenario. Those are determined statistically based on the material properties and based on the parameter that you're setting on the machine. Of course, if you are closer to the optimum process parameters, you're gonna get a less scatter, and if you're far from that one, you're gonna get a higher scatter. And basically, how they are translated there is again, how much porosity you have, and even another driving factor is that especially when you're talking about a more complex loading scenario, then it depends. You can see that the worst case scenario is when you have like a large porosity or a large inclusion right in the highest stress location that you have, right? Imagine that, yeah, you have your weakest point on the highest stress location. That would be your worst case scenario. But again, you are not determining that one. That is determined statistically.
All right, thank you very much. Let me check the questions and see if we've got any more that have come in. Oh, okay. Let's see. Can you point us to the title of the journal paper that you published on this?
I can actually, if the title, I forgot, it's been a couple of years. um, let me stop sharing and try to find that one so I can share back and show you that one. How much time we have? Okay, we have a couple of minutes. Give me 1 second.
All right. All right. Thanks everyone for your patience while Bruce
Okay.
pulls that up.
Right, I find it here. Let me share back again.
Yeah, no worries. No worries.
Okay.
All right.
There you go. This is the paper. If you want to get snapshot of this one, and in the title, and it is in the Journal of Tribology.
All right. Thank you very much. And also, we will be posting this recording to the America Makes YouTube page, so you can always go back there as well if you're interested. All right. Let's see. I think I might have. Oh, okay. I think I missed a question here. So I think we have time for another one here. So, how is the porosity predicted? Is it through empirical calibration as a function of laser parameters?
Yes, so it is actually, yeah, it is through those, yeah, it is caused by the caused by the process parameters, but they are translated to the microstructure through those thermal simulation and through those thermal history. So because of those thermal history, if there is, again, not enough power or too much power, it is translated to porosity, and then the porosity is formed. As you saw, the grains are formed, the porosity is formed between them, of course.
All right, great. Thank you very much. All right, I think that's all the time that we have for today. Bruce, could you bring up your presentation again and just put that last slide on there so we can get your contact information out?
Okay.
All right.
There you go.
All right. Thank you very much. All right, so that's going to wrap up today's TRX webinar series. I would like to once again thank Melissa and Behrooz. That was a great presentation. If you have further questions for them, please reach out to them directly at the email on the screen there. Also, there will be a post-webinar survey going out to all of those who participated. We really do appreciate the time that you take to provide America Makes feedback so that we may continue to improve and strengthen our additive community. And as a reminder, if you think you or your organization will be interested in sharing in the TRX webinar series, please fill out the form that follows the presentation, or you can reach out to me at jason.thomas@ncdmm.org. Thanks, everyone, and have a great afternoon.
Thank you very much.